So we know standard representation, what these representations look like. Let's start to look at what are some nuclear reactions that we can do. And I'm going to start with the really simplest ones. This is the first nuclear reaction that we ever had at the beginning of the universe, right? When we first started creating elements. How do we make the elements of the periodic table? The answer is through nuclear chemistry, right? Protons combine with other protons and other stuff happens from there. Okay, so we're going to get into this and we're going to talk about how do we think about these reactions? What does it mean to balance a nuclear reaction? All right, so these are all going to be examples of nuclear fusion, right? We're going to take two nuclei and fuse them together and see what happens. So we're going to take two hydrogen atoms. So in the way back in the beginning of time, right, all we had in the universe were hydrogen atoms. And eventually those hydrogen atoms got forced together so closely together that they fused, right? So we have one proton plus one proton, and you would think, okay, so one proton plus one proton equals two protons. And of course, you would be wrong. That would be far too easy. And so what we get out of this is we actually get a hydrogen nucleus, but you get a proton and a neutron, right? And the reasons for that are we'll get into that here in just a little bit when we talk about stability, but notice that this is not balanced, right? In order to balance a nuclear equation, whoops, that's not how you spell balanced. Balance of nuclear equations. Right? So we've been balancing redox equations and you've been balancing chemical reactions for a long time. This time we're going to balance a nuclear equation. This is very easy. The two things we have to do is we have to balance the mass and we have to balance the charge. Right? So in this case, if I take a hydrogen plus a hydrogen and I get out a hydrogen 2, right? Hydrogen 1 plus hydrogen 1 gives me hydrogen 2. The mass is balanced, right? We have a mass of 1 for the first hydrogen atom. We have a mass of 1 for the second hydrogen atom. We have a mass of 2 over here. So we don't need to add any more mass, right? No more mass there. But the charge is not balanced. We have +1 for the first hydrogen atom, the first proton. We have +1 for the second hydrogen atom, this proton. And we only have +1 so far. So to balance this out, we need a +1 over here. Now we have a +1 as a charge and we have no mass. This is one of those special particles. We go back, this is a positron. And so what we create when we combine two hydrogen 1 nuclei under the right conditions is we get a hydrogen 2, this is hydrogen 2, plus a positron. Okay, so at this point, someone always raises their hand and say, how do we know that we make hydrogen 2 and a positron? Like if you just said H1, hydrogen 1 plus hydrogen 1, how would I know what the other side of the equation is? And the answer is we don't really have uh, or we're not going to get into too much how to predict what the actual products are. We'll talk about it a little bit, but for the most part, this is one where you're going to kind of be given enough information to kind of balance the rest of it, right? This isn't something where I'm going to ask you to come up with the products without any other information. Okay, so we get hydrogen 2, which is a proton and a neutron, plus a positron, and that balances this equation out. Now, hydrogen 2 can combine with, notice that we really haven't made anything new. We've just made a different isotope of hydrogen. This can combine with another molecule of hydrogen 1, and we end up with helium 3. Now in this case, notice that we don't have to add up, we don't have to do any more balancing because the charge, 1 plus 1 is 2, and the mass, 2 plus 1 is 3, are already balanced out, right? So we just take the top numbers on the product side or reactant side, take the top numbers on the reactant side, add them up, and see if that matches our product side, right? Here, 1 plus 1 is 2, 2 plus 0 is 2, we're good. Down here, 2 plus 1 is 3, and we have a 3. And we do the same thing for charge, right? So the bottom number is charge, we have +1 plus +1, and that gives us +2. And so we're almost done, but we've made helium 3. Helium 3 is not the most stable isotope of helium, right? And so what's going to happen is we're going to have two molecules of helium 3 come together, and they're going to make helium 4. and they're also going to make 2 molecules of hydrogen 1. And again, I'm just kind of telling you this without having to go through too much of what our overall equations are, or how do we figure out that it makes 2 hydrogens and not a molecule of helium-2, for example. Right? The reason that we know this is these are the nuclear fusion reactions that happen in the sun, right? Um, at the center of the sun, the hydrogen atoms are pushed so close together that they undergo these fusion reactions where we create hydrogen 1 into hydrogen 2 into helium 3, and then helium 3 into helium 4. Okay, so all of which is great. So basically this is a way to convert hydrogen to helium, right? And so at the beginning of the universe, these are the kinds of things that happen. In the center of the sun, these are the kinds of things that happen. Nuclear fusion is the thing that powers the sun. And then eventually, right, as the sun gets older and older, the helium atoms start to get pushed closer and closer together. And those helium atoms combine to make beryllium or carbon. And then those carbons combine to form iron. And like you keep kind of moving up the periodic table. And of course, in order for this to work, the sun has to get denser and denser and denser, right, to force these atoms together to make them react. And so the life cycle of a star is to start with very light elements like hydrogen and helium, and slowly convert them to more and more heavy elements until eventually the elements are so heavy that they can't be compressed any further. And then they start repelling each other. The sun explodes, right? You get supernova and all that other fun stuff. So this is how we get heavier elements. It's all nuclear fusion. Now we can add all of these together, right? So I'm going to do a little bit of funny math here just to kind of put all this together. If we add up everything on the reactant side and the product side, we have helium-2s on the reactant side and the product side. We have hydrogen-2 on the reactant side and the product side, right? And so if I multiply this equation by 2, is that what I want to do? Wow, whatever. When I add these all together, what I'm going to end up with is 4 hydrogen atoms, 4 hydrogen 1 atoms on this side. Yeah, I think I need to multiply both of these by 2. I got it now. 2 times all this stuff and 2 times all this stuff. This is the right one. Because now we've got 2 hydrogen 2s on both sides. We've got 2 hydrogen 3s on both sides. And so the helium 3s will cancel. The hydrogen 2s will cancel. We'll be left with only hydrogen 1. We'll have 6 hydrogen 1s on this side and 2 hydrogen 1s on this side, which comes out to 4 hydrogen 1s. And those are going to convert to 1 molecule of helium 2 plus 2 positrons, plus a whole bunch of energy, right? Because this is what the sun makes. So in the center of the sun, in the core of the sun, this is what's happening. We're having 4 hydrogen atoms turn into a helium atom, plus some positrons, plus a ridiculous amount of energy, right? And of course, this is what Einstein figured out. And this is the energy that comes out of this is predicted by what happens in these fusion reactions. And so what Einstein noticed is that if you take a proton, which has a mass of 1.0073 atomic mass units, and you take a neutron, which is 1.0087 atomic mass units, and add them together, you would expect to get the mass of hydrogen 2, because hydrogen 2 is a neutron and a proton. But notice that we started with 2 protons here. And so there is a difference here in the mass of what we expect and what we get. So hydrogen 2 ends up having a mass of 2.014 atomic mass units. And if you add all this up, of course, you get 2.016. And so there's a difference. So proton plus neutron equals 2.016 atomic mass units. So what's going on? Where does that mass go? Conservation of mass says that we should always have, right, the same amount of mass. We should be balancing that. And what it turns out is that mass is converted into energy. And so what we need is we need an equation that will relate the amount of energy. So we have a difference in mass here. The amount of energy is equal to that difference of mass times something. And it turns out that that something is the speed of light squared. So equals mc squared is really this nice thing that comes out of um, these nuclear fusion reactions, where it's noticed that the weight of a proton, the mass of a proton, the mass of a neutron don't add up to when you have a proton and a neutron together, which is very strange. But the reason that that works out is because what we get is we get this outpouring of a huge amount of energy, which is, of course, why the sun radiates so much energy. And so this radiation is, of course, one of the main outcomes of nuclear chemistry. Is all these reactions always produce these weird defects in mass, and that mass that disappears is converted into energy at a huge, right? You get a huge amount of energy for a very, very small amount of mass because you're multiplying everything by c squared. So when we do all these reactions, we're always going to be kind of producing these huge amounts of energy and all that other kind of stuff. Okay? So that is balancing um, balancing nuclear equations kind of in two different ways, right? One way that we balance it is we balance the mass and we balance the charge in broad terms. The other way is we recognize that there are differences in these masses and that that difference in mass is accounted for by E equals mc squared. And so we get huge amounts of energy whenever we do nuclear fusion reactions or nuclear fission. Either way, it's going to work. Okay, on to the next one.